All right, let's go ahead and go over this. What are we looking for in this question? We're looking for a volume. All right, so I need a volume. I've got a volume unit right here, and I've got two pressure units. And I start with a pressure of 40 millimeters of mercury, and I end with a pressure of 60 millimeters of mercury. So I'm increasing the pressure, so what is that going to be doing to the volume? It's going to go down. So then I'm going to just put 12.3 liters here, and I'm going to put 40 millimeters of mercury here, and 60 millimeters of mercury here, because if I put them in that orientation, the millimeters of mercury are going to cancel out, and I'm going to get a smaller number than 12.3. So what number do I get here? 12.3 times 4 divided by 6. 8.2. Good with that? What's happening in the next one? What are we looking for? I'm looking for the volume again, and I have a volume unit, and I've got this gas at 25 degrees Celsius. It's at 1 atm, and then it goes to 2.5 atm. So what's different about this question?
That's temperature, volume, and pressure.
Okay. How does that affect the question?
That's one increase and the other one increases.
The temperature is ancillary information, right? Did they mention anything else about the temperature? They just said it was 25 degrees, right? So we don't need to worry about that temperature since there was no temperature change. Okay, so it was at 1 atmosphere and it went to 2.5 atmospheres. So again, we're just crushing this thing, right? So I've got 3.6 liters, and I've got 1 ATM and 2.5 ATM. The ATMs cancel. I got 3.6 divided by 2.5. I get 1.44 liters. Okay. The next one. Again, I'm going to be looking for volume. So looking for volume. Got a volume unit right there. So I need to manipulate the temperatures. So what happens? Does the liter number get bigger or smaller? It gets bigger, right? What I'm doing is taking this thing and heating it up. And so since I heated it up, what will a gas do when heated? Expand. So what's the first thing I should do though? Definitely go to Kelvin. So 273 and 273. So I've got 600 milliliters, and I'm going to put my 293 on the bottom. I'm going to put 333 in the numerator. That way I get a bigger number. So 600 times 333 divided by 293. I get 692. No, I don't. 682 milliliters. Okay. All right, so I've got same situation here going on, right? Milliliters going into a temperature. The temperature goes up, so 273 and 273, so 900 milliliters. And then I've got 403 and 300. Oh yeah, sorry. 405. 1215. So really 1220 milliliters for SigFix. Determine the pressure change at when a constant volume of gas is going from at 1 atmosphere is heated. Okay, so again we're heating this thing, and so if I increase the temperature on something, what happens to the pressure? It goes up. The molecules of gas or atoms of gas are hitting the container harder. So 273 and 273. So 1 ATM. And so 303 and 293. Yeah, 1.03 ATM. So that was a bunch of gas law questions, and we never once did what with them? Use any equations. Never bothered with the equation. Don't need to. You just need to know what the relationship between those different parameters are. One goes up, how that's going to affect another one. Complete the following single replacement reaction entering products and states. Okay, so CDO and an N, and so solid, aqueous. No, that's not going to be aqueous, is it? That's going to be a solid. And then this is going to have to be a solid. I'm going to need a 2 here, and a 7 here, and a 7 there. Are we good with that? No questions about that one? So this question was a little bit different than the other questions that we had before. I just wanted you to stop at the number of moles instead of going all the way out to grams. So I've got silver chloride and I'm reacting it with, what am I reacting with? Copper? Oh yeah, copper. And I want to know how many moles of each product will be made. So it's the same kind of question, we're just not going all the way to grams. So 243 grams of copper, 63.546 grams of copper, 1 mole of copper. Oh, and I got to do something first. I got to write copper solid plus AgCl solid turns into CuCl2 and silver. So I'm going to need a 2 right there and a 2 right there. Why is it copper 2 chloride? That's the one that's, if you look on copper's oxidation states, there's 2. There's a 2 and a 1, and the 2 is bold. So unless you're doing something weird, it's going to be copper 2. It's like copper 2 90%, 95% of the time. Okay, so I needed to do that because I needed a balanced chemical equation for this. So I'm going to go with 1 mole of copper would give us 2 moles of silver. Okay, so then I'm going to do the same thing again with 275 grams of silver chloride. 1 mole silver chloride, 35.453 plus 107.8682. And so I get 143.23, no, 321 grams of silver chloride. And then for every 2 moles of silver chloride, I have 1 mole, no, 2 moles of silver. All right, so 243 divided by 63.546 times 2. And so this is 7.6 mole. And then 275 divided by 143.321 dymole. So what do I know?
Why are they both silver? Don't you want to know copper too? Moles of copper?
No. Why do I want to know moles of copper?
Well, it says how many moles of each product.
Copper's not a product. Copper's a reactant. Okay. Plus, how do we do these problems? What's the first thing we have to do? You have to see which one runs out first, right? So how do you determine which one runs out first? What are you forced to do? Solve for the same thing. If I don't solve for the same thing, then I have no idea which one ran out first. So I solve for the same thing, and then what's it telling me now?
275 grams of silver chloride made
The most silver that I can make, given these two reactants, is 1.9 moles of silver. Why?
because you only have 275
Okay,
silver
what happens?
runs out.
The moment that you've made that 1.9 grams of silver, you've got no more silver chloride, so you can't make any more silver. So that means that there's going to be a bunch of leftover copper. So then we're going to do one more calculation, right? We'll start again with the silver chloride, and this time we're going to go to the other product, which is the copper 2 chloride, and then we'll calculate how many moles of that copper 2 chloride will be left. So it's 275 grams of silver chloride. 1 mole silver chloride. 143.321 grams of silver chloride. And then for every 2 moles of silver chloride, it's 1 mole of copper 2 chloride. Okay. Well, I just need to divide by 2, right? My last answer. Yep. Take us at 0.96. So is that first calculation that we did useless? It's not useless, it's just, it needed to be done. How come it needed to be done? I needed to confirm that the silver chloride was going to run out first. But after I've confirmed that the silver chloride runs out first, then that first equation is kind of meaningless for the rest of the question. I have to do it to determine which one's going to run out first, but after that, then I don't need to refer to it at all. Because I'll never be able to make 7.6 moles of silver chloride with what I was given, because my silver chloride's going to run out way before that. Okay. Combined gas law, I'm going to solve it for T2. Okay, so it's P1, V1, T1, P2, V2, T2. I'm going to solve it for T2. So T2 equal to P2, V2, P1, V1, T1. So the T2 goes to that side, the T1 goes to that side, and the P1 and V1 go down to the other side. Does the way that this is set up make sense? How unit-wise does this answer make sense? Yeah, the only unit that's going to be left with it like this is the temperature unit, which is good because I'm looking for a temperature. I can't have any millimeters of mercury talking about an answer with my temperature. So the pressures and the temperatures both cancel out, leaving me with temp, or the pressure and volume, sorry. What is the final volume of 300 milliliters of gas that's subject to a temperature change of 12 and pressure change? Okay, so I've got a volume and I want to know a new volume. And I've got a temperature change and I've got a pressure change. So that's combined gas law. But really we're just going to use the railroad track. So I'm going to start with 300 milliliters. What happens to the pressure of this during the course of this change? The pressure goes down, right? So what would that do to the size of a container when the pressure is released on it? It should get bigger, right? So I'm going to put 750 millimeters of mercury up here, and I'll put 360 millimeters of mercury down here, because that's going to give me a larger volume number. What's going on with the temperatures? They're also, well, the temperature's going up in this case, so what's that going to do to my, the size of my gas? It's also going to make it get bigger. So 273 and 50 and 273 and 12. So I'm going to put 232K here and 285K here, and I'm going to get a bigger milliliter number. So 300 times 750 times 323 divided by 285 divided by 360. So I get 708 milliliters. All right.
Can we go back one? I have a question.
On
On the silver color.
yeah.
So on the other railroad tracks that we were doing, we had to add the grams.
We always went to grams.
Right, but, should we have another row with the grams of, like, silver?
We would, except I specifically asked you for moles.
Oh, okay.
That's the only reason that we didn't do it the way that we've done the other
That
way.
is-
Gas pressure is reduced, volume of the container is increased. What's the final temperature going to be? Okay. So I got a temperature, it's gases, so I'm going to go 273 here and get 3. So I've got 383K. So the pressure of a gas is reduced. So what relationship do pressure and temperature have to each other?
Direct.
Direct, right? So in this case, the pressure, or sorry, the pressure went down. So how, if the pressure went down, what should the temperature be doing? The temperature should be going down. So I'm going to put my 750 millimeters of mercury here, and I'm going to put 1,000 millimeters of mercury here. And then I also have the volume of the container is increased. So what's the relationship between volume and temperature?
If it increases, it decreases.
Also direct. So I have an increase in volume here, so that relationship to the temperature would be an increase for the temperature. So then I'm going to take the bigger number, my 320 milliliters, and on the top, and 75 milliliters on the bottom. And so we'll get 383 times 750 divided by 1,000 times 320 divided by 75. 2, 2, 5, 6K, and then minus 273. Why did I convert it back into Celsius?
That's what the answer is.
I started in Celsius, so that's your responsibility as the calculator to put the units back to what they were if you were given units. And if you needed to convert, you need to go back to where you were. So I guarantee you on a standardized test, answer A is going to be 1,226. And answer D is going to be 952. And A is wrong. Temperature of a gas in a steel container is 50 kilopascals. It's increased from 2. Okay. So the relationship between temperature and pressure, if the temp goes up, the pressure goes up. So I'm going to take my 50 kilopascals, and then I'm going to take my small number and put it in the denominator. So this is 273. So that's 2100. Okay. Is that good?